Welcome to this session on competing risks. And here we are going to understand about the concepts relating to these competing risks. So, especially in any single one life. So you have any single one life, um, any single one life. If it's subjected to more than one decrement, for example, a normal life person, he can leave that state of normal either because of retirement or because of death. Or a healthy state person, he can leave the healthy state either because of illness or because of death. So whenever one single life is subjected to more than one decrement, where in that particular life can leave the population because of more than one set of risks, we call that situation as a situation of, or all those decrements as a set of competing risks, right? So this is an example. And whenever we see competing risks, we generally resort to two kinds of mechanisms. So the first one being the multiple state model, the multiple state model, modeling. So here we use the mechanism where we use multiple state modeling, where in the various concepts relating to Kolmogorov differential equations. So look at the Kolmogorov differential equations will be used for solving the probabilities part. And two, just like the life table approach, for the life table approach individual life, we will look out as the multiple decremental table for these competing risks. Now let me focus more on this multi-state model itself. So here let's say I talk about a three-state model, very common application, right? So a person A is in an active state, he may move to a retired state or to a death state. The same could be talked about in respect to sickness also. Instead of retired, I can bring in the sickness. The only difference being here is that from an active state he is going to a retired state. Let's say the transition intensity being sigma x. From an active state he is going into a death state with a transition intensity nu x, and from a retired state he's going to death state with a transition intensity nu x. Here there are no other modes, because he can go back to the active or retired, or from the retired state he can't go back to the active state. Whereas if I'm looking at the, instead of retired here I put sickness, then there is a possibility, so this is the possibility of one more line going back from sickness state, he can go back to the active state. So different kinds of state depending on the states. This is this transition diagram that we are getting into, this transition diagram we are getting into can much vary. So here I talk about the three states. So the states are A, R, and D. And anytime I talk about the typical transition intensity for an edge x to edge x plus t, if I'm talking about, let's say, AR, what does this mean? The transition intensity from state A to the state R by the time he reaches the edge x plus t, that is what we are calling as a transition intensity, which means if I'm really supposed to compute TPX, let's say AR, it's as good as the probability that the person is in state R at time x plus t, given that he's in state A at time x. So this is what is the meaning of TPX AR, right? And right here, A and R are different states. So the probability that the person is in state R at time x plus t or at age x plus t, given that he is an active person at the age of x. But the same thing if I write TPX AR with a dash over it. Okay, let's say AA. So if I put AA, then I'm saying AA. So when I'm saying TPX AA, let me say if I'm writing TPX AA, this means that the probability that a person is active at time x plus t, given that he is active at time x. Okay, but nowhere it is mentioned between about x and x plus t. Probably he could have gone to retired and come back to the retired state and to the active state. Imagine it is a sickness. So we are talking that the probability that is in state A of x plus t, given that he is in state A at x, because he can't come back to so this is the same as the probability that he is in state A to x plus t. So when I write it like this, TPX AA means that he is in state A at the age x plus t, given that he is in state A at the age x. But when I write it as TPX AA bar, it means that the probability that he is in state x to x plus t, given that he is in state A at x, means that he did not change the state in the middle, or he has been there for that state only. So this means that if the return to this particular state is impossible, once I leave this state and I can't come back, in that case I can very well say that TPX AA is the same as TPX AA bar. For this kind of a model, I can very well say that TPX AA is the same as TPX AA bar, because once I leave the state A, there is no way I can come back to the state A again, right? But in some cases, probably if you look at this model, let's say active, sickness and death. So this is the ASD model. From active to sickness, I can come back from sickness to active, from sickness to death, and from active to death. So let's say these are the transition matrix or transition intensities. So once I leave, so here TPX AA is not the same as TPX AA, but the reason being, there is a possibility that he can come back from there's a possibility that he can come back from state S to A. But when we are talking about AA bar, he has been in that state only and he has not moved. And he has not moved from the state A. So when there is a possibility of returning back to that state, once it leaves, then these two cannot be equal. Otherwise I can try to very well equate them, these two equations, by trying to understand what is the difference between this and this. And now to solve them, we know the Kolmogorov differential equations, right? We have the Kolmogorov differential equation, d1 over d1 of t. So the forward equation that we have said, t px from state G to state H, it is nothing but I'm trying to TPX times Gj times nu x plus t nu jh. So it is as good as I can take it as a matrix. So TPX times Gj multiplied by nu x plus t, it means that for j not equal to h, so this is for j not equal to h, I'm doing the summation, and it should not return back, so that means I'm saying TPX GH has already reached the state H, and from there it is returning back to some other state J. That probabilities we are taking out. So this will be the typical formula for the d1 over d1 of t, TPX GH. Whereas for GG, so this is d1 of t, TPX GG bar, we know that is nothing but minus TPX G bar times, I'm doing a j not equal to g nu x plus t gj, and this would result in a closed form solution e to the power of minus integral 0 to t mu x plus s ds. This is from G to J. So this would have given us a direct solution for our TPX GG bar. And if we have some model like this, we can talk about the computations of the present values of the death benefit for a person who is alive, or I can talk about the sickness benefit for a person who has been alive now, or all kinds of computation can be done in the same. So let's look at this model. The active sickness death. Let me compute some basic calculation on the top of this model. So from A to S, the transition is sigma x, and then from the bottom one is it's rho x. Here, let's say the transition is mu x, and here the transition is nu x. Now I'm talking about a lump sum benefit of one that is payable on death. So either the death can come directly from an active state, or a person, he could have gone from active to sickness, and then from there he could have gone to death. Okay, so let's look at the overall, or the overall probabilities for that. So let me assume that from active state he has gone to death, which means I'm interested in finding out TPX that is in state active only at up to x plus t, and once he's active, from there he's gone to death, mu x plus t. Similarly, he has moved from state A to state S by the time he goes to x plus t, and from this state S, he died. So he has died, so it is nu x plus t. Now this is the typical present value. This is the typical present value. So this is the expected value, and I'm finding the present value, so I have to multiply it. I have to multiply this whole thing by e to the power minus delta t. So this is the present value. So we need to integrate this, then e to the power minus delta t. So this whole thing will give me the expected present value of the death benefit. Right. Similarly, if I'm looking at the active in case of the sickness, what is the sickness part of it? So it's TPX. So this is active and sick. So from x to x plus t, what is the probability that he is in state S, given that he is in state A initially, and I'm paying a benefit of 1, and I want to find out the present value of it. So this is the present value, and I'm integrating it from 0 to infinite. This will give me the expected present value of the sick. And all these can be very well simplified using the Kolmogorov differential equation mechanism. So there could be closed forms when we are going with Kolmogorov differential equation mechanism. But this is where sometimes I can bring in, apart from the dependency of the Kolmogorov equation of this multi-state model, we can also talk about multiple decrement tables. In this context, we can bring in the multiple decrement tables, wherein we introduce few new terms, A, Q, X. Probably here I'll say R means retirement. What do I mean by this? It is the probability that the person who's currently aged X, right, he would be removed from this current state, whatever the state he is in or is there, between the time X and X plus 1 by this decrement called retirement. Even if the other decrements are also present, means even if death is present, this is the probability that he will exit the population because of retirement. Whereas the same thing when I say QXR, it means it's independent. So this is the dependent probability, and this is the independent. So this is the probability that a person who's currently aged X will move out of the population between age X and age X plus 1 because of the decrement R, assuming that there are no other risks as in that particular population, right? So this is what we are trying to understand when we look at the multiple decrement table, and a few important concepts that come into picture. Let's try to look at A, Q, X, D being the death. All we are saying is that the probability that the person in state active, he is leaving the population because of death. Now let me assume that retirement and death are the two decrements that are there. So I go with this ARD kind of a model, right? Let me look at the ARD model, where we are talking about from active to retirement. We have sigma X. Active to death, we have nu X. Retirement to death, we have X. Now AQ X is nothing but, given that the retirement is also there, the probability that the person who will leave this particular state will leave this particular state X because of death. Now if I'm saying that AQXD, I can very well, so the probability of a person who is age X is there, who's currently in an active state, within a year, via the decrement of death, is the same as the probability of death in 1 year's time. So if I assume here, let's say this is means this is not there, means this transition is 0. what is I'm saying that AQXD, the probability that the person whose age X will leave the population because of death is the same as the probability that the person who's currently in state active moves to the state death from age x to x plus 1. So these two mean one the same. So AQXD is the same as PX A to D. This is one important relation if there is no other transition operating, right? If I assume that if this is 0, then this is an important relation that is coming into picture. And now we can really try solving out AQX. If we are to in reality, let's say AQX R as well as AQXD. How are we able to solve? So let's look at the differential equations from the Kolmogorov part. We know that TPX from active state to the retired state. So let's look at this. So we know that the round of TPX from active state. So it is from I have to go from active to active multiplied by new, and then active to retired. This is active to retired. It's coming out as sigma, and from here I can go to retired in any form. So I'm subtracting TPX. I'm going from active to retired, and from retired coming to death part, and the only transition is nu x. So we know that the germ of T over TPX AR is the same as TPX AA times sigma minus TPX AR times nu. And we know that TPX AR, right? If I want to know TPX AR, which is nothing but AQX. So this TPX AR, so we know that TPX AR is nothing but AQXR. If at all the nu is equal to 0. So if nu is going to be 0, probably it's because the retired state is an absorbing state. So the probability that a life whose age X leaving the state A active through the decrement or retirement before the age X plus T is the same as the probability that the same life is in the retired state at the age X plus T, because it is an absorbing kind of a state. So which means from here I could very well get T and then AQXR. So I can write as rho d round of T AQXR So this part is not existing. So it comes out as TPX, then AA sigma. And what is TPX AA? We have already got it as e to the power of minus summation of all the transition intensity. So towards the retirement, where is the retirement? It is sigma, and towards the death it is nu. So I can write it as e to the power minus sigma times t. So this whole entire thing comes out as sigma times e to the power of sigma plus nu into t. And the same kind of a solution I can get with respect to AQXD also. Similar kind of solution if I want for T AQXD. I'm getting a similar kind of a for mu times e to the power of nu plus sigma t. Now I've got these two things. I can very well substitute t equal to 1. So if I substitute t is equal to 1 from there, I can solve these differential equations. So AQXR becomes sigma over sigma plus nu, then 1 minus e to the power of nu plus sigma. Similar, I get AQXD as nu over sigma plus nu. Then I have 1 minus e to the power of mu plus sigma. Mu plus sigma. So I can use these relations to solve or how I compute with case of a transition matrix given. I can very well compute my AQX or AQX of R and AQX of D. Both of them I can compute based on the transition intensities through this mechanism. And so we have got the differential probabilities now. We have got what? We have got AQX of R as well as AQX of D. And now we also know the QX, which are the independent probabilities. So if I'm talking about the QX of R, I'm talking about the moment, that is moment coming from A. So I'll take it as e to the power of minus sigma. Similarly, if I'm talking about QX of D, I'll call it as 1 minus e to the power of minus nu. Now that I have AQX and QX, right? So probably if I'm looking at 1 minus of AQX of R minus AQX of D, right? So we know that AQXR, so this is AQXR. Similarly, an AQXD, this is AQXD, so you got it as nu over sigma plus nu, and then you get this factor. So if I sum up these two, if I sum up these two things, I'm getting this as 1 minus e to the power of negative nu plus sigma. So this gives us, when you further simplify it, you get e to the power negative nu plus sigma. So overall it is working out as minus nu plus sigma is equal to the log function of 1 minus a q x r minus a q x d. This is x a q x d. So this negative here, so this comes like this. So from here we can very well so nu plus sigma is coming out to this much. Yes, from here it is working out as let's see, okay, if I'm taking it the other way, it becomes 1 minus e to the power of minus nu plus sigma. This is equal to aq xr plus aqx d. So aqx, we've got it. So from here I can say that aqxd is nothing but so aqxd is nothing but nu over n 1 minus aq xr minus aq xd. So nu divided by sigma, so get this as so this also becomes a q x r plus aqxd xd. So I'm able to find aqxd in this particular form. So from here I get the value of mu. So mu comes out as aqxt. So in 1 minus aq xd then minus what, a q x, so this is supposed to be r and this is d. divided by, so this is my mu, so but yes, so this is how I get so D. So in so how do you get QXD? So QXD is the same as 1 minus AQ XR minus AQ XRD to the power of so this becomes the power of AQ XD divided by AQ XR plus AQ XD. This is what to come out as QXD. And if I'm talking about QXR, instead of D it becomes R. So if it instead of D here it becomes R. So this is the typical relationship we can convert between QX and QR. So these are the independent probabilities because of the decrements, and any kind of numericals can be worked out accordingly. So this becomes a 1 minus AQ XR minus AQ XD to the power of AQ XR over AQ XR plus AQX. So these are the kind of expressions that are there in a multi-four decremental table. Once I have the dependent probabilities, I can link them with the independent probabilities and vice versa through these different kinds of relationships. And the comfort and the usage of all these different relationships is very much important to solve the numericals that are existing with the multiple decrement kind of tables, right? So if you're not very clear about these things, you can go through the notes which I'll upload as well, but I advise you to go through these and try to understand them as well. So I'll also upload some notes regarding or just some additional information on this video as well on the portal. So thank you for attending the session, and I'll see you in the next bit.